This is the component 2 mock, and this is Holy Cross mock number 1. And question 8, parts of a seashore. Any of you going on the biology field trip will wander up and down a seashore, and the tide goes in and out, and some organisms live at the top where they don't see much of the seawater, and some live down at the bottom. We have a table of data, and you've been out in an environment. You went out and you counted organisms, and you did this with quadrats, and you collected data like this, and you worked out indexes of diversity. So you've done all this, and you just need to do it again. Use the formula, there we are, in super micro print, to calculate the index of diversity for seaweeds growing at site A. I'm going to do it on this bit of paper here just to make it look bigger. So our equation for Simpson's diversity index is 1 minus the sum, so add up all of the little n minus 1s, and divide that by big N minus 1. Okay, and this is for site A, so equals 1 minus so what are the n minus 1? The n is the number of the individual species. So for example, the n for Ascophyllum nodosum is 2. So this would be 2, and then in the brackets 2 minus 1. So it would be 2, and then 2 minus 1. And the sum means add them up, so we'd add that onto the next one, which is 10, and then 10 minus 1 in the brackets. Add that onto the next one, which is 4, and then 4 minus 1 in the brackets. And then add that onto 6 with 6 minus 1 in the brackets. The rest of it would stay the same, and big N is the total number, and so what's our total? It's add these together, so that's 22. 22 total is 22. So 22 and 22 minus 1 on the bottom. So we just need, I'm going to do this step by step. Some people can do it faster than this. So 2, I'm just going to solve the brackets. So 2 minus 1 is 1. Plus, I've got my 1 minus 10 with 9 in the brackets, 4 with 3 in the brackets, plus 6 with 5 in the brackets, 22 with 21 in the brackets, and equals 1 minus 2 times 1 is 2. Plus 10 times 9 is 90, 4 times 3 is 12, and 6 times 5 is 30. And then you might remember to keep this 1 separate from any of this. And 22 times 21 is 462. Okay, and so add these together at the top. That gives me 134 divided by 462 equals 1 minus, so put that into your calculator, that gives you 0.29. So 1 minus 0.29 gives us 0.71. That's a lot of work to squeeze into this little area. You might be able to do, cut out some of these steps if you're clever, but that's the way I'd do it. So there's my working out and my answer here, 0.71. So not as diverse as the other area. And does that answer look sensible? Does this area A look to be less diverse than area B? Well, it does. There's less species, so you'd expect that. So it kind of looks right. Give one advantage of calculating this index rather than just recording the number of species present. So number of species 4 and 5, 6, 7. Well, this index takes into account the number of individuals present in each species as well as the numbers of species present. So they're kind of weighted, because you might just have one individual of a species present just by chance, and that would skew if we were just counting number of species, but it'd have less weight in this index. And so we would have, it takes into account the numbers of individuals, so it takes into account the numbers of individuals as well as the number of species. And we are now looking at a graph where they have taken some seaweeds. This is one of the experiments that one year we actually did on the field trip by hanging up seaweeds on a washing line. So what they do is they take the seaweeds, and we've got Fucus spiralis, so that's more of a spiral shape, and serratus fucus, so serratus more of a kind of serrated like a saw. So that's where they get their names from. And what they do is they leave them for a while and keep weighing them. So after an hour, they weigh them at the start, and it's got 100% of its mass. Then they keep weighing them every hour, and they're losing mass by water via evaporation. And we can see that Fucus serratus loses a lot of its water mass, a lot quicker than Fucus spiralis, and it loses more of the water. So it does it quicker and it loses more. Explain how the results shown in the graph relate to the distribution of these two seaweeds on the seashore. Well, we'd expect a seaweed that doesn't lose a lot of mass, being kind of better adapted, for being in a sort of drier environment, whereas the seaweed that essentially doesn't care about whether it loses mass or not, because it's wet a lot of the time, so further down the shore. So we would expect spiralis to be up at site A more, and serratus down the shore. Now, our evidence for that, we need to incorporate evidence from this table. So Fucus spiralis loses less water and loses it less rapidly. You could talk from either the point of view of either one, but I've gone with spiralis here. As lost less mass. So the graph is actually showing mass, and we are relating that to evaporation of water. So Fucus spiralis is better adapted. To being exposed to the air, better adapted to being exposed to the air, drier conditions for longer. Why? Well, it needs to conserve water because it might need that for its metabolism, or to avoid, death by desiccation. So some suitable reason here. So needs to, because we need to relate it to the distribution, needs to conserve water for example, metabolism, or some other reasonable suggestion there. Why can it be up there? Well, it can compete better up at the top if it can retain its water. So this means it competes better in drier environments because it's better adapted. There are a couple of other things you could say there, but that's probably enough there. And you could say the reverse argument of this. So Fucus serratus loses more water, and so it's better adapted for living down at the shore, nearer the sea. And that's just 6 marks for all that work. Oof.